of lecture 9. In this lecture, I will be focusing on an application or a use case of CL-PKC. Once again, I'm Eugene and I'm taking charge of this lecture. In this use case, we would consider a secure smart parking application, which we'd refer to as SSP. This is basically a simple lightweight secure communication protocol which is based on CL-PKC. The main idea behind this is to secure the communication between a parking drone and IoT devices deployed on registered cars to monitor parking. Without a dedicated PKI or public key infrastructure, the scheme can be applied to relatively resource-constrained devices. In this use case, we have the KGC, a parking drone, and registered cars which house IoT devices. The SSP application has a set of 8 algorithms, some of which are very similar to what we discussed in the previous lecture on CL-PKC. So we have the setup algorithm, which is the same as what we have in CL-PKC. We have the set secret value algorithm, which is similar but modified. We have the partial private key extract algorithm, which is also similar but a bit modified. The set full private key algorithm, which is the same as what we had in CL-PKC. The set full public key, which is modified. And then we introduced 3 new algorithms: the symmetric key gen algorithm, the encapsulation algorithm, and the decapsulation algorithm. Now we proceed to describe all these algorithms to give you a better understanding of how they work. So we have the setup algorithm, which is same as what we had in CL-PKC. Basically, you have the KGC taking as input a security parameter, generating a set of parameters G1, G2, and E, computing P, computing the MSK as S, and then computing P0, which is its public key. After that, the KGC chooses 2 hash parameters, H1 and H2, and then publishes the parameters and keeps the MSK secret. The parameters basically are G1, G2, E, P, P0, H1, and H2. And like I mentioned, they're publicly available. Now we have the set secret value, which is executed by either the drone or the IoT device on the car. It takes as input the publicly available parameters and the identity of the user. Computes XI and computes PI. Now, unlike what we had in CL-PKC, where the set secret value algorithm just outputted the secret value, this one, the algorithm for SSP, outputs both the secret value and then the public value, both of which are partial. We have the partial private key extraction algorithm, which is also executed by the KGC. Takes as inputs the parameters, the MSK, the secret key, the identity of the user, the public key of the user, and the time constraint, which is used to limit the validity of the partial private key and partial public key. Now the KGC chooses a random value Ri, computes big caps Ri, computes the partial private key Di, then outputs both Di and Ri. They have the set full private key, which takes as input the partial private key generated by the KGC, and then the secret value generated by the entity itself. Outputs a full secret key, which is a combination of both partial keys. We have the set full public key, which takes as input the partial public key received from the KGC, and then the partial public key generated during the set secret value algorithm. Outputs the full public key. We have the symmetric key generation algorithm, which is executed by the entity who wants to initiate communication in a secure manner. So it takes as input the identity of the sender or the executing party, the full private and full public key of that entity, the identity of the recipient, the full public key of the recipient, and then the time constraint. Now, the entity chooses Li and Hi, computes U and V, computes Y, which takes as input the identity and full public key plus time constraint, computes T, and then computes the key, which is going to be the session key, which is going to use to secure the communication between the entities. Now, obviously, it outputs the key. We have the encapsulation algorithm, which is as well executed by the entity who generated the symmetric key. Takes as input U, V, and T from the key generation algorithm, identity of both the recipient and the sender, full public key of both recipient and sender, and the ciphertext. Now, this ciphertext is basically the encrypted message, where the message is what you are sending to the other recipient, and the encryption is done using the key that was generated in the previous algorithm. It basically computes H prime and W, and outputs the encapsulation parameter, which is UVW. The encapsulation parameter is sent to the recipient. Now, upon receipt of this encapsulation parameter, the recipient also takes as input the ciphertext, its full private and public key, the identity of the sender, and the time constraint. Compute Y, compute T, compute H prime, and then is able to compute the key that was used in the initial encryption, or the key used in the initial encryption. Now, mathematically, this has been proven to mathematically correct or accurate. Now that we are done with the algorithms, I'll try and break down the use case into 3 stages or 3 phases. We have the car registration phase, which we have a car and a KGC. Now, the car generates its own security value, X, and public key, PI, sends its identity and public key to the key generation center. Upon receipt, the key generation center computes the partial private key and partial public key, and sends these back to the car or the IoT device on the car. Upon receipt, the IoT device is able to generate its full private and public key. Note that the full private and public key, the partial private and public key are valid for a set period or set amount of time. Let's say, for example, 12 months in this instance. The next phase is the drone pre-patrol phase, which is before the drone goes out to patrol a parking area. So we have the drone, we have the KGC. The drone generates its own secret value, XD, PD, sends its identity and public key to the KGC. KGC computes the partial private and partial public, sends these back to the drone. Upon receipt, the drone is able to compute its full private key and full public key. Now, like that of the IoT device on the car, the partial private and partial public key are valid for a set amount of time. For this instance, we'll assume it's valid for just the flight time, let's say 30 minutes or 1 hour. Now, this is the main phase of the use case, where we have the drone patrol. So a drone is patrolling a parking area, looking for all the cars parked and trying to communicate with them. The drone continuously broadcasts a message, M1, which contains its identity, public key, full public key, and time constraint. Now, whichever device or whichever IoT receives this message generates a key, a session key that's going to be used to encrypt all messages that's going to be sent to the drone. The IoT device computes a ciphertext, which is basically an encryption with the generated key of, let's say, the location, permit, and time, and then it encapsulates the ciphertext to output the encapsulation variable. Now, when this is done, the IoT device sends M2, which basically contains its identity, its public key, the time constraint, the encapsulation parameter, and then the ciphertext. Now, when the drone receives this, the drone is able to decapsulate the decapsulation variable to output the session key, and then uses the session key to decrypt the ciphertext, verifies the data or the message encrypted with the key, and then is able to decide whether the car has violated a parking arrangement or the car has a valid parking permit to be in a particular place that is. This is basically the application of or a use case of CL-PKC. Now, if you are interested in reading more about CL-PKC, we provided links on the Moodle page as well as here, which go to 4 papers. Certificates Public Key Cryptography, which is like the genesis or the main material on certificates public key cryptography. A secure communication protocol for drones and smart objects. Arrows in a Quiver, which is a secure certificates group key distribution protocol for drones. And then we have Footsteps in a Fork, certificates fork-based access control. Both Arrows in a Quiver and then Footsteps in a Fork are in-house papers that we use certificates protocol, certificates cryptography to design secure communication protocols. Thank you for your time. If you have any questions, as always, you can send an email to myself, eugene.frimpong@tunu.fi, or you can send an email to Antonis. Thank you.